Okay. Before we start the course, is there anyone named Stephen? Stephen Lee? I just want to know your student ID. Anyone? Uh, Name Stephen? Stephen Lee? Okay. 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 Anyway, let's start the course. Okay. We can start with the question from the feedback. Okay. This is about the Ferris wheel and asking uh, so if you have a Ferris wheel, it has certain rotation speed, radiant speed, and the question is how fast is a rider rising? So the key is the key word is rising. Okay? So rising, if you are imagine in the picture, it should be from the bottom to up, right? So it's about the height, the rate of change of height. Okay. So if this is a Ferris wheel, like maybe this is the cart, right? So it's moving like that. Okay. So we want to know how fast the change, for example, from this point one to point two. It's actually you can pinpoint in any point you want in Ferris wheel, as long as it's describing there is a change in height. Okay. For example, if I write like this, the h here, and I know that I need to evaluate when the total height from the ground is 16 meter. The question is provided you with those information, so 16 meter above ground level. And what is dH over dt? That's basically the question. So we can answer that by looking at the triangle. So this is h, okay, this is h, this is let's say x, okay. And we know that when h is equal 6, then x is equal 8. Okay? We know this from the information, and we have the formula. I think the formula that we can use is the sign, because we want to know the h, and we have 10 as our fixed point or fixed number, right? So we will have this as our relations, and then we can derive that. So derive, and we get uh, from sine, we get cosine, and then d theta over dt and dh over dt. And we get from dh over dt is actually, so the d theta over dt is pi, right? From here, from 1 revolutions. 1 revolutions means it's rotating in a full circle. So it's 2 pi, and it's every 2 minutes. So it's by precisely pi radian per minute. So the rotations. So we are just plug in all the information, and we got 8 pi. Uh, I think two of you got correct. I want to know who is answering this. I want to write down your name. Can I know who write this one? I want to know the student ID. Anyone here? Do you remember what the answer? Can you write down your maybe ID in the chat box? Oh, okay. Hands. Okay. 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 Thank you. Uh, the next one is about the plane, or maybe I will give it this notes first. Okay, for you to read and maybe taking notes. Oh, okay. Okay. Stephen Lee, can I know your student ID? Okay, let me write here. Okay, thank you, Stephen. Okay, I think we can move to the next page. Still the feedback questions. Now it is about there is a plane. Okay, there is a plane. It flies horizontally, and it has certain height or altitude, and passing over a tracking telescope on the ground. Uh, so when the angle of elevation is pi over 3, this angle is decreasing at a rate of pi over 6. How fast is the plane traveling? So it's asking, so if this is maybe some x, so what is the dx over dt? Okay, we know the angle decreasing at certain rate. What we need to do is carefully drawing the diagram. Okay, so carefully we draw. For example, this is the plane. It's going in horizontal. It has 5 kilometers as its altitude. And the question is asking when the angle of elevation. This is if you don't really understand what this angle means, your drawing will be a little bit not perfectly correct within this information. So the angle of elevation is if you have plane like that, this is the horizontal line. The plane of the angle of elevation is the angle that is inclined in between this horizontal. So it's going, the plane is going into a certain height with a certain angle. This is the angle of elevation. So the angle of elevation is we need to be careful and make sure that we confirm the angle is from the horizontal line at the ground. So this is our angle here. This is angle of elevation. And then the question is asking when the plane is here, okay, when the plane is at this angle, what is the rate of change? How fast, right? How fast the plane is traveling. Okay, we can see from here we are having a nice triangle. So we can use the triangle this pi/3 angle here, right? We have x, we have 5 altitude because the plane is just stay at same height, okay? So we can use the tangent. So tangent 60 is 5 over x. Okay, that's our relation here. Okay. And then we know that when we have the angle 60, we also know that the other cosine and also secant for the value for our calculation. So from this tangent here, we can write down the relations. Tangent theta is 5 over x. Okay, then we can derive from here. Okay, we can derive. Yeah. Derive, we get product rule. We get product rule. This is the results. The question is asking this dx over dt. And we may have the secant squared here. That's why I need the secant here to put into this information. Okay. Our x is also can be evaluated from the tangent 60. So we get 5 over square root of 3. 4 is from secant. This is x. This is the angle d theta dt. And this is the 1 over tangent. So we are having it's around 10 over 9 pi kilometer per minute. Let me to make it more clear. Maybe I will write down one by one. This is here. So and then this become here. Okay, let me give you some time for maybe taking notes, or maybe also if you want to ask questions from these two related traits. Okay. So related traits, we are move away from here, and we already have the linearization. I will make a little bit review what's the linearization in a quick review, and then start with chapter 4 today. Okay. Okay. Okay, Oliver, I will see your question. Uh, okay, to apply the protocol. The composite functions in order to apply the product rule. Okay, so basically the idea is taking this taking this relations is actually the important thing in all related traits questions, is how to connect with all the quantified parameters and then connect all into one single formula. The way you are connecting is you need to know at least a few known, like geometrics, trigonometrics, or inverse trigonometrics also you can use. Geometrics like an area, volume, triangle. Triangle means you can have like law of cosine, Pythagorean, and some triangle property. That basic formula you need to know beforehand. And of course, if I give you related rate problem, and if I'm not sure that you know the formula, I will give the formula in the questions. Okay, so that's the idea. So to know how to get this, so first you need to identify this diagram. Okay, so we need to identify the diagram really well. Okay, so for example, if we read the question here, from the question itself, it has directions to note that it has the altitude of 5 kilometers, and it just say it passes directly. It doesn't say there is a change in the height, right? So we just assume, okay, it's just stable, not really changing in height. Okay, but it has an altitude of 5 kilometers. So 5 kilometers is our constant. It's fixed at that point. Okay, it doesn't change. Okay, the one that change is when the angle of elevation is pi over 3, the angle is decreasing at a rate of pi over 6. So it has something changed here, right? This will be our variables. Okay, so in related rates, everything related to variables, we will involve this d over dt. It can be the angle, it can be the change in distance. We will have ddt in everything that change. Okay, so that's the idea. And then it's asking at the elevation at pi over 3. So we have at a short amount of time, at that moment, if you remember the uh, it's called the instantaneous rate of change, or in our terms in calculus we call it tangent, right? Tangent at, let's say, at a, or if you remember this terms here in calculus, the first derivative. Okay, so the first derivative here, it suggests us to, okay, we have something that changed and we need to derive that. Actually, that is the idea behind the related rates question. So we need to identify which one is constant, always the same, okay, fixed value, like 5 kilometers is always 5 kilometers, it doesn't change. And then we also identify the variables. This, for example, in this case here is the change in angle. So ddt over d theta over dt. That's the one that changes. And we need to connect all these things, right? We know the angle is changing. So we may have this triangle here. Okay, we have that, let me draw maybe here. We have that at certain theta, we have some decreasing rate of change, right? So we have theta here, and we have something that is fixed. And the other, we can make our name, make our own name. For example, this may be x. Okay? And I think this is enough because we know the theta, we know the constant. So we take this as our relations. So we need to relate the angle, x and 5. And I think the better way doing that is using the tangent theta. And so that's why I'm using tangent theta 5 over x. I think in case of trigonometry, you can just choose between its inverse or tangent. Okay? I think it depends on some cases. Maybe it will be faster doing the inverse, or maybe it's faster doing trigonometry. It depends on the case. It depends on the case. But I think for this case here, Okay, I will just use the tangent theta and equal 5 over x, or we can simply simplify, become x tangent theta equal 5. And then every time you have these relations between all the things you have in related rates, the next thing you need to do is derive. Derive with respect to t. You get all dx, from here you get the product rule, and then dx dt, blah, blah, blah here. Okay, the rest is just simple calculations. The idea, the difficult things here is to identify. So we need to identify which one is constant, which one is changing. Okay? It has a rate of change. Okay? I hope that helps. Okay, Oliver. Okay. Okay. That is about the related traits. I think you will have more, maybe some example in with TA, with teaching assistant. And maybe if I have time to give you some practice, maybe later if we have time. But let's continue. Okay, I think I want to start with the just quick review about the linearizations. Okay, so linearizations is basically, okay. So maybe first we are start with the definitions of uh, limit and derivatives. We have this, right? So in linearizations is actually we are going to observe, or we are observing that the derivative or the tangent is actually approximating the secant. Okay, so this means the tangent is basically approximating the secant. If you remember the secant line in the tangent line and secant line, so when x near a, right, the gap is small between f of x and f prime a. So we can take the approach and we have another equation called the linearizations. So what's the difference between these two? This is not the same, these two. Okay. The difference is we call this is approximation. We are going to use this formula for evaluating the exact value approximately. Okay. The second one is more of the linear equation at A. And you're going to notice that it has difference in here. Okay? The first one is described approximately, okay, not really exact number, but approximately approaching some number. The second one is precisely the equations, okay. But it has the similar principles, okay. Similar principles, we can say that. Okay? It has similar principles, almost similar meanings, but it's different. Okay? So if you are asking, find linearization of, you have a functions at maybe some a equals something, that means you are going to get linear equation y equal maybe mx plus c. So you need to have equations. Approximations, usually you are use it for estimating value. Okay, estimate value. Okay. Okay. Now from here, okay, just keep in mind this formula. I will going move to another problem. I think I already gave it to you. This is a physics problem, and you may know how to work in to working on. So let's say the s is our position, okay, with variables t. Okay. It's t cubed minus 6t squared plus 9t, and then you are evaluating from 0 to 5, and then there are only two questions asking average velocity and asking average speed. Okay. Now, first we need to know the difference, okay, between the average velocity and average speed. Okay. Okay. Average velocity and speed. Do you know what's the difference? So what is average velocity? Do you know? Something over something. This is also something here divided by something. Anyone know? Or still remember in physics? What is average velocity? You can check your physics notes. Velocity has a factor. Okay. Okay, but what is the meaning? Okay, what is the meaning? Displacement over time. Okay. 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 If I write average velocity as change in displacement or change in positions, right? And divide by time. Okay. That will be average velocity. So you just yes, correct. Average speed, total distance traveled, right? Divided by uh, time, okay, or total time. Okay. Now from here, I will use calculus to analyze, okay, and hopefully I can relate this to our chapter 4. Okay. Chapter 4 is about applications of derivative, especially uh, to illustrate a graph, okay, to sketch a graph, and also to identify from graph. Okay, now we can check. Okay, we can check the results. So let's say we need to have results on velocity from the definition. We know that change in positions between 0 to 5 is s5 minus s0, the displacement, right? The change in places, and then divide by 5. Okay. If you look at the functions here, let me just write the function here. This will be s5 125 minus 150 plus 45. 45 minus 25, it's 20, right? It's 20. So it will be 20 divided by 5. It is around 4. If s is in meter and time is seconds, so we can write this as meter per second. Okay. Okay, that will be our average velocity. Now we move on to average speed. Average speed total distance traveled. Let me just write traveled divided by total time. S5 divide 5. Yes, yes. S0 is 0, right? Oh, yeah, yeah, yeah. So total distance traveled, okay, we can check, okay, uh, if we know the S5 is 20, S0 is 0, we need to make sure all the distance the person has, because we are not sure when or is there any like uh, time to stop and maybe he turns back, okay, because if you really care about the functions is having a cube. A cube. A cube means it can be like that, or it can be like that. It's also cube. And of course, if you have cube, uh, probably you will have a certain point that the person will turn back, and we need to know where that is. Okay? The easy way to find out is uh, right here, as t is t cube minus t squared, 60 squared plus 90. The easy way to know is we need to check our derivative. Okay? We need to check. And how to check when it's going back, it turns back, is if we remember the graph. Like for example, if we have this, okay, we know that this is going up, the gradient is positive, and here's the gradient is negative. So if we have, or if we know the slope, when slope is 0, we know that there will be a certain time that the person change positive to negative or from negative to positive. Okay, so we can check using our first derivative, right? And take it as 0, because we need to know when the person will going back. And we can simplify this, and we get this is, we have t equal 3 and t equal 1. Okay, what does it mean here? We can check S1. Okay, S1 is 4 meters. So this is 20 meter. This is 4 meter. And then S3 is, I think, 327. Yeah, it's 0, 0, right? 27 minus 27 is 0. So it gets 0 twice, which means that the person is back into the first position, right? Okay. So if I draw in a line number, okay, the first one start from t0. Okay, that start from here. The person is going to run. Okay, and maybe here he's moving to t equal 1. Let's say this is 4 meter. So this is 0, 4 meter. And then uh, instead of move forward, he is going back. He's going back. And then it's t equal 3. Okay. So he moves 4 meter and then he turns back and traveled 4 meter. So 4 meter plus 4 meter, already 8. And then from t equal 3 to t equal 5, maybe he is going to run, right? He's going to run. And then 20 meter. So this will be 20. The total distance traveled will be 20 plus 4 divided by total time is 5. So it's about 28 over 5, or it's 5.6 meter per second. So that will be the total distance traveled. Now we are going to observe, okay, at this point here, t equal 1 and t equal 3. So imagine the person is going to move here, okay, this 0, and then some distance, and then going to distance equal 4 meter. Okay, I reach 4, and then he turns back. Okay. So he changed the direction, and then reaching 0, and then change again the direction. So probably the graph is something like, maybe he's going here, and then going down, and then going up. Probably that is our graph. I am drawing a little bit random here, but if we are thinking that this is the change here, maybe this is the when the m is 0, this will be maybe t equal 1, right? And this will be t equal 3. You see, it's going up, and maybe it's decreasing, decreasing, decreasing until 0, and then change the directions become negative, and then move back again, move forward, and change direction to positive. Okay. Now to identify this curve, how when the person turns back, what is the maximum value, minimum value? That will be our discussion in chapter 4. Okay. So usually we call this point here, the slope is 0. We call turning point. We can also call this critical point. I think the most common is critical point. We can also call this a stationary. And we can also call this, this will be a local max, and this will be our local minimum. There is also another terms called absolute and absolute minimum, absolute maximum, or global maximum, global minimum. Okay, but I think I will just keep one terms because in textbook it is using just that term. So we have absolute max, absolute mean. Absolute is if in the whole domain of the functions it's the highest, then it's max. If it is the lowest, then it will be mean. But if you are maybe for example, the total graph is like this. Oh, maybe that's really clear. Uh, oh, Oliver, I think negative and positive, it depends on you. For this case, okay, for this case, why I'm using positive negative, just to note that positive mean the distance is added, so the person is going forward, but going backwards, maybe I will use the negative. Okay, this is just to give you an illustrations. Okay, illustration. You will know later in more details how we can identify and maybe uh, taking some notes on uh, the critical points precisely. Okay? Okay, so if we have this kind of graph here, okay, if this is the whole function, okay, if this is the whole function, okay, if this is whole functions, means the domain is from here to here, okay, from this A to B, then we call this will be local max. This will be global or maybe absolute max. And we can directly call this absolute mean. And this will be local mean. Okay, just keep in mind these terms. Okay, we are going back to elaborate in more details. Okay, the maximum and minimum value. Okay, but to start chapter 4, I would like to start with 4.2. Okay, 4.2, not 4.1. 4.1, I will start after 4.2 because 4.2 is related to what we have learned in chapter 3. Let me give you some time here. And if you have any questions, you can also ask. Okay. Okay, we are continuing this session. Okay, now I will start with the chapter 4. This is applications of differentiation or derivative, you can call that. Or simply, this is how to sketch a curve using a calculus. Okay, I will start with a theorem. It's called uh, the mean value theorem. Okay, so the mean value theorem, we need to start with Rolle's theorem. Let me write first. Okay, let a functions satisfy three different statement or hypotheses. Okay. Function is first continue on this closed interval, and functions is differentiable. Okay. Differentiable on open interval AB. Uh, and the second one is FA equal FB. Let's start with the Rolle's theorem first. It says that when the function is satisfying these three components, there is a number C in between AB such that f prime C is equal 0. Okay. Okay, maybe this. So this is A, this is B. FA and FB need to be the same height. Okay. So we will have the slope 0 here and slope 0 here. Also, maybe another possibility is the function is just line, horizontal line. That's also possible. Another case is maybe this one here, maybe that. Maybe that is our possibility for the shape of the graph. Okay. So we will have something in between AB that is actually, we can have, for example, this one, we can have C1 and C2, right? We can have 2C that is equal 0, and this is f prime C equals 0. Okay, so basically what the Rolle's theorem say, if you have a function that is continuous, differentiable, and it has AB that is equal, okay, certainly at the very middle or in between AB, there will be at least one C that is f prime C is equal 0. You can have one or maybe two, or it depends, maybe three is also, it depends on the function, but at least one number C that is the f prime C is equal 0. Okay. And you can have the maximum value, minimum value from those f prime C equals 0. Now, you have this theorem. And the second one, okay, we will give you we will discuss this mean value theorem. So first you have this Rolle's theorem. Okay. Okay, the next one, let me give you the mean value theorem. Okay. And we are going to see what does it mean. Okay. The first statement is similar with the Rolle's theorem. So let f be a function satisfies the following. The first, f is continuous on closed interval AB, and f is differentiable on open interval. Okay. There is a number C in between this AB. That is, you have f prime C is equal. I hope still remember the formula that I previously wrote down in linearization. Okay? In linearization, or we can simply solve this. Now, to make out this in any sense. Oh, before that, I hope you know why the let me write here in clear. Do you know why? First, we have two statement, two first statement in Rolle's theorem and also mean value theorem. First is the function continues on closed interval. The second one, differentiable. But differentiable is open interval. Do you know why I need to make these two as different? Okay. If you remember, if I have this graph, okay, it's the absolute value x, right? The functions. The function is continuous, right? The function is continuous. But if you look at this point here, it's not differentiable. Okay. So that's why the differentiable one is not at the end of point. Okay? Because here is actually we don't know what is happening here, right? If it's still in domain or not. That's why we need to write in the open interval and the continuity in the closed interval. Okay, that's the idea. Okay, now here there's a number C in between A, B. So if we are uh, going to look at and maybe taking some random functions, maybe just that. Okay, it's not too smooth. Let me make it more smooth. Okay, maybe that is our random functions. Okay, let's say we have this point here is A, f of A, and this B, f of B. Okay. From here, I will connect A and B, the endpoint here, and this will be our second line, right? Our second line. Or in terms of the physical problem we have, this will be our average velocity, right? This will be we can say that this is the average velocity. If you imagine this as time and also positions. This will be displacement over time, right? If you are having t as your variable at the very beginning, our physical problem, okay? Or we can say this is a secant line, okay? Now we know that this is our secant line. If we draw the tangent and how we are going to observe, we can start maybe from here, the tangent here, the tangent here, and then eventually it will be here. Okay, and then we can also see the tangent is also changing here, here, and changing. Okay, maybe it's that, and maybe changing again here, here, and yeah. From this picture, we are going to see that our second line, okay, if we take this first tangent, okay, this tangent here, maybe C1 and then FC1, okay, and this other tangent here, the second tangent here is C2, FC2, okay. If you look at how the slope is, we know that the f prime C1 or C2 is the same as the secant line, okay? So we can write f prime C in general, okay? This can be C1 or C2. We can just write this FV minus F of A is equal with the average velocity, right? Remember that the tangent means the instantaneous velocity. The rate that change in a short time or in precisely that seconds or that t. Okay. Okay. So we can also say that the statement here or here, okay, the statement here, this means is there exists a number c whose average rate of change is equal to instantaneous rate of change. So from Rawls theorem and now the mean value theorem, it's now becoming clear that there is a number in between that is uh, the value of average rate of change and the instantaneous rate of change will be equal. Okay. Now, why I want to start from the mean value theorem, not from the 4.1 about maximum minimum value, because I want to start with uh, something that connects with the chapter 3, which is this formula here. And will be the key in our chapter 4, this formula here. Okay. So from Rawls theorem, it's being perfected by the mean value theorem. So mean value theorem is we can say uh, it's confirming the Rawls theorem, and it's applied in more general rules. Okay, so that's the mean value theorem. Okay. So now from this f prime c or f prime, we can have consequences of f prime c. We can have consequences if f prime is positive, if f prime is negative, and if f prime is 0. So if f prime positive, it will be increasing. Function is increasing. This is decreasing. This is constant. Maybe I will stop here for you to take some notes first, and then I will take the next page for another notes. Okay. Okay, let's continue. Okay. Now let's continue and elaborate more in the formula and the consequences. Okay. Let me write the uh, the expression of the mean value theorem. Okay, if the A is less than C, C is less than B, and A is less, of course, less than B, and if the B minus A is positive, okay, then we can rewrite this FB minus f of A. This will be equal f prime C, B minus A. And we can write in terms of FB, that is f of A plus f prime C, B minus A. Okay, if we know the B minus A is positive, if this is positive, okay, then I will write the consequences, what we have done before. First, if f prime C is positive, okay, so if this is, maybe here, so if this is positive, okay, then the FB, okay, then and FB will be greater than f of A. Second, if f prime C is negative, so if this is negative here, if this is negative, okay, so it will be FA minus something, right? Of course, it will decrease the amount, and we can say that FB will be less than f of A. Okay. And if f prime C is equal 0, then it might have that FB equal FA. Okay. So this, if this is 0 here, if this is 0, then FA is equal FB, right? Okay. Okay. So this will be the consequences. And if we compare, okay, if we compare, oh, maybe I will write in the next page. Okay. So let me give you time to think on these consequences. Okay. So from the consequences here, then we can move to the consequences when the function is increasing, we will have the maximum value. And when it's decreasing, we will at least getting some minimum value. Okay? So from here, then we can go to extreme value theorem. And I will show you what's the uh, applications for the mean value theorem aside from these consequences. Okay. Of course, we can use the mean value theorem in some applications, at least for proving proving some statements, some mathematical statement, or some proof. Okay. Okay. Now, if we compare, okay, comparison, so linear approximation, we have delta f delta x. It's approximately the f prime at a. We need to have b is near a. If we remember the previous one is I write this expression. Okay, or if you remember last week, I write x near a. Okay, here I will use b near a. Okay. I hope you still get the idea. And b minus a will be the delta x. In mean value theorem, this is linear approximation. In mean value theorem, this delta is equal with the f prime c. Okay. So there will be some number c in between a and b. Okay. So we can write this, okay, the ratio we will have minimum value and maximum value. Okay, maximum value. We can also compare this comparison with the average speed, right? Average speed. This is, you have minimum value, also maximum value, and you can also approach this approximately with this instantaneous. If you approach with the linear approximations, this is mean value theorem. Okay, this is just to show you what we have learned. Okay? Linear approximations, mean value theorem. So because it has similarities. Okay, that's why I'm eager to start with the mean value theorem. I hope you don't mind. Okay, for this mean value theorem. Okay. Okay. Now, how to apply the mean value theorem in some certain case? In some certain case. Okay, let's start with some a few example that I have in mind. Okay, the first one is I have a statement: e with the power of x is greater than 1 plus x, and x is a positive number. And then how to prove this? Okay, to start with, we have this inequality, right? So to prove this, we can look back in our terms of cases here. Okay, what the consequences have? Okay, so first, if the f prime is positive, we will have fb greater fa. If f prime negative, we will have fb is less than fa. If f prime is equal 0, then fb is equal fa. That is basically what we are going to do. So we need to define our functions. Okay, we need to define our functions. So first, define the functions. So let of functions is equal. Let's say we have this e to the x minus 1 plus x like that. And that will be our function. Okay. And to start with, because x should be positive, at least 1, or maybe some fractions between 0 and 1, why we don't start with the x equals 0 to see what the functions look like, okay? To see what the functions look like. Okay? Let's say we check with f equals 0, because it's easy to do, right? This will be resulting in 0. Sorry. 0. Okay. So if we have, okay, if we have uh, f equal 1, let's just say f equal 1, this will be e minus, this is 1 plus 1. Okay. We still have a positive number. Okay, we don't really need to account or calculate the exact number here, but we know that this will be positive. And if we increase, x is also positive. Okay. Okay, so let's check our expressions in terms of first derivative. We get this is e to the x minus 1. Right? And from the idea here, if we check with 0, 1, 2, 3, this is also resulting with greater than 0. If we check x equals 0, check x equals 1, it's always a positive number. So what does it makes the conclusions? So what's the conclusions? So remember, if you have fb, fa plus f prime c, and then b minus a. Okay, if we know that, for example, b and a maybe 1 and 2, or maybe 0 to 1, or 0 to 2, or maybe 2 to 3, any positive number, okay? So we know that b is always greater than a. Right? B always greater than a. Right? So this will be a positive number. Right? It's always positive number. And if we know that f prime c is positive, okay, it's positive, then for sure, we know that FB is always greater than FA. And that means, okay, that means that our inequality, f of x, e to the x, is always greater than 0. Or proven that e to the x is always greater than 1 plus x. Or if you want to write like in a complete way, you can say that because b minus a and f prime c is positive, so f of x will be always positive. And by conclusions, you can write that ex or e with power of x will always greater than 1 plus x. So mean value theorem, you can also use it for solving some inequality problem. Okay, another idea on how we are going to use the mean value theorem is proving, or maybe simply to check how big our number will be or how small our number will be. Or let me show you the other one. For example, suppose you have 3 less equal f prime x less equal 5 for all x. The question is show that 18 less equal f of 8 minus f of 2 less equal 30. Now, using the mean value theorem, we can at least giving some solutions to work on. Okay, to work on. So at least we can write first the mean value theorem. And we can have this fb minus f of a okay. And then we know from the question we have at least to evaluate f at x equal 8 and x equal 2. Okay. So probably what we need to do is we need to let a is equal to and b is equal to 8. Okay. Then at least we have f of 8 minus f of 2. This will be equal to b minus a is 6, so 6 f prime c. So we have this equation now. And then we also have the f prime inequality from the questions, right? So it follows that our f prime x is in between of 3 and also 5. Now, if we look here, we may have some number that if we are looking at this 3 and 18, 5 and 30, it is a multiplication of 6, right? So why don't we try to multiply this with 6? So it will be 16 less than 6f prime of x, and this will be 30. And we know from our previous equations that 6f prime is practically the f of 8 minus f of 2. Then we know that, let's say this is equation 1. So from equation 1, we get that 18 less than 6f prime x. Let me write this first. And then this will be equal. And basically, this is what we are going, or we have been proving. So we are having this inequality proven. So proven that this is true. Or you can write the QED. Okay. Okay, any questions first before we continue? Actually, there is several theorem from the mean value theorem that, but I think it's just simple logic in the function, so not really useful theorem. Okay, I think we can move to, now we will move to 4.1. 4.1. Okay. Because we already have at least learned the mean value theorem, we can now have a consequences of maximum and minimum value. We call that extreme value theorem, extreme value. So we call this extreme value. And I think most of you already familiar with the minimum value, the maximum value. I think once you learn the functions, you know that there is a point that is usually you call vertex or minimum value or maximum value. I think since you are a junior high probably, and it is always repeated in high school also, and now you learn one more time. But now we are going to observe and analyze the theorem and the graph the functions in a more related to the calculus. Okay, so we need to analyze every steps, every theorem. Okay, so axiom value theorem, we can start with the if the functions continues on interval AB closed interval, the function has both a minimum and maximum value. Which means that if you are having just like this function like that, you know that this is the minimum, this is the maximum. In general, we will going in more details. Okay, this is function, okay. And sometimes we call maybe like that. Okay. We can have this is absolute maximum. If this is the whole domain, okay, the whole function, this is the absolute minimum. This is our local max, our local mean. This is when f prime of c is equal to 0. This is f prime of, maybe we can have name A and then B, okay, close interval AB. This will be C and this will be D. So this will be f prime D equal 0. Okay. We call the f prime is our critical point. So C and D is our critical number. C, F, C, and D, and then F of D is our critical point. And then from this graph, the local max and local mean, it shows us that there is another theorem. It's called the Fermat theorem. If the function has a local max or minimum at some number C, okay, then the functions of C exist, and then the f prime C is equal 0. This is the consequences on the slope that we already take a look on the mean value theorem. Okay, so f prime is 0, which means that there will be a local maximum or local minimum at that point. Okay. And then to get through to the next theorem, we're going to show you some graphs that what we are going to observe. Okay.
Professor,
Yes.
can I ask a question?
Yes.
So the local max is like a second largest value or something? What is the
Oh, yeah.
definition of it?
Okay. So, okay. I think I need to. Yeah, I haven't give you more detail here. So sorry. Okay, so for local max, every time you have a slope that is positive and change to negative, you call it all with local max, actually. Okay, actually. And when you have this negative and becomes positive, you call that a minimum. Or you can say just maximum minimum value, that's okay. But to differentiate between local and absolute, okay, absolute is when it is largest or smallest in its domain. Okay, so the key is this domain here. So if the whole domain, the value will be the highest, then it will be the absolute maximum. If it is the lowest, then it will be absolute minimum. For local, so, okay, for local, we say local is we just only looking at certain region. Okay, like for example here, oh, this will be the maximum here, but it's not the highest one. It can be a second, it can be a third, it can be a fourth. As long as it is changing the slope from positive to negative, we call it maximum. Okay, so basically every time you see this, it's actually local maximum. But when you're looking in the whole details with the domain, you know the highest and the lowest, then that will be the absolute. You can say that. So you can say that the local max is generally every maximum and minimum value. You can call them a local maximum and local minimum, generally. Okay? But if you are including the whole domain, then you need to make sure which one is the absolute one. Okay, I hope that's clear. Okay.
So we can have a lot of like local
Yes, we
max.
can have a lot of local max and local min. Yeah, we can have a lot of.
Okay, thank you.
Yeah. Okay. Fermat theorem. Oh, I need to show you just a graph to keep in mind, and then to show you. Uh, for example, I have this graph. Okay, let's say this is a whole domain here. Okay, so this will be our absolute max. Okay, but if we have hole here, a hole, okay, then at this very hole, we don't call this absolute minimum in the hole. Okay, so absolute minimum might be in between this, okay, but not in the hole. Okay, that's I think pretty clear that we have. This is the function is on interval, open interval AB. If also if we have in limit we have learned the asymptote. If we have the asymptote, like for example here, and then we have this is maybe C. This is from A. Let's say this will be B. Okay. Imagine C and D is close, and then you have the like asymptote here. Okay. You have an asymptote. And also we call this, in this hole here is not absolute max. Okay, it's not absolute max. But here we can call this B is maybe this absolute minimum. Okay, this is just something to keep in mind. So every time you see a hole or maybe asymptote, that will be important in our observations too. Okay, last graph that I want to show you, and maybe last session in our course is let me draw maybe a large graphs. Okay. Start from this. Start from that, and then continue. Okay. Maybe this will be make it similar, so you see that this is actually similar height. Okay. Well, let's break down this graph here. Okay. What we are having. So if this is the whole function, the whole domain already put through in this function, this will be our absolute max, right? Of course, we are clearly see that this is the highest one. Okay? And let's name the point. Okay, let's name the point. This is, let's say, start from x0, x0. And we know that the slope at x0 is 0. Okay. Now, we see that we have also our local mean here. This is a local mean because there's another absolute that is lowest, right? But we call this local minimum. Let's say this is at x1. Okay, f prime of x1 is equal 0 here, the slope. But here, what is this? This point. It's also maximum, right? Because we clearly see that the gradient is from positive and change to negative. So we know that this will be our local max. But then, what is f prime? X, let's say x2, right? The f prime, if you remember the differentiable functions, then this is not differentiable. So this is not equal 0. Or we can say the f prime at x2 is undefined. And then if this having a slope here is equal 0, the slope is 0, let's say this is equal, let's say this is x3. So f prime x3 is 0. But is it maximum or minimum? It's not max or min. Okay, so not necessary to be max or min, but the f prime is 0. Okay, and maybe at the end of the graph, that will be our absolute minimum. Okay. Okay, I will stop here and we will continue precisely from this graph next Friday. Okay. So this is quite interesting graph because sometimes when we learn the calculus, maybe in high school, we know that if we have f prime, some a or some x is 0, then this is our critical number. But it's not always the case. It's not always the case. Okay? It's not always the case. Okay. Okay. Any questions before we move to feedback time? I'm just preparing 2 questions for feedback. Okay. Okay. If there's no question, then we can move to feedback time and we can start our evaluation. Okay, we can scan the QR code and uh, maybe going into the website. And hopefully you still yeah, later, okay, at the end, Laura, or the QR code. Okay, okay, let's start. Okay, let's start. 3, 2, 1. Okay. Okay, so I hope you still remember the linearization. Okay, so yeah, if you're confused about the questions, it's asking linearizations, but the terms in the options is f of x. So f of x needs to equal something. So you need to remember which formula has the f of x at the beginning. Okay, 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 good. If get ready for the next question. Okay, okay, 3, 2, 1, let's start. Okay, read the questions carefully. Okay. Okay. 5 seconds. Okay. I hope you still remember and get the answer. Okay. Okay, good. I think most of you got the correct answer. Oh, good. Good job. Good job. Yeah, that is the end of our lecture. Let me go back to the QR code. Okay, if you haven't scanned the QR code, this is the QR code. So if you can scan now, if you haven't. For the rest of you, you can leave the Google Meet link and see you next Friday.